Hello all, this course is on the lecture 2 which is vehicle dynamics. So, the course is week 2 lecture 1 which is on vehicle dynamics. The basics of vehicle dynamics, what is the importance of vehicle dynamics and why exactly we need to study vehicle dynamics is what we are going to look in this course. So, initially what this vehicle dynamics is it actually tells us about what are the forces that are acting on the vehicle when the vehicle is on move. So, when vehicle is moving, we observe that the vehicle is just moving, but we do not know what is happening internally or what are the other forces that are actually acting on the vehicle. So, this vehicle dynamics will give us an information on how or what are the forces acting on the vehicle. Now, why do we study this? So, the main reason why we study this forces acting on a vehicle is we need to calculate the torque and the power that is required by the motor when we are designing an electric vehicle, or in case if we are designing a ICE, even then we need to know the torque. So, in order to know the torque calculations or in order to know the power of the motor or the engine, whatever it is, we need to understand what is the force that is required and what is the torque that is required to oppose all the external forces. So, in that aspect, if we see, this is a very important topic and we start with it by understanding what are the different forces that are acting on a vehicle. So, this is what a vehicle looks like. Now, when the vehicle is moving, it is observed, as you can see, it is observed that there are various forces acting in and around the vehicle. So, around the vehicle, the major forces that are acting are, the first one is the aerodynamic drag. The aerodynamic drag is nothing but when the vehicle is moving, the air will be hitting the vehicle. So, this air or the opposition to this air should be provided by the vehicle in order the vehicle to move. Next one is the rolling resistance. So, when you have the wheels when moving on a road will have some friction. So, this friction also should be overcome by the vehicle. So, the second one is the rolling resistance and the third one is the hill climbing resistance. In case if the vehicle is moving on a uphill, now when the vehicle is moving on the uphill, the force, an external force or the extra force should be given to the vehicle so that it moves the inclination, and it is almost proportional to the gravitational force along with some angle of inclination. The next force is the linear acceleration. So, the force which is required to move on a normal road. The next one is the angular acceleration, and all these together combinedly we call it as the tractive effort and it is denoted by FTE. So, FTE is the sum of the aerodynamic drag, the rolling resistance, the hill climbing resistance, the linear acceleration and the angular acceleration. So, these are the different types of forces that are acting on a vehicle. Now, when a vehicle is moving, the power or the torque, whatever you call, the complete vehicle should overcome all these forces. So, we will deal with each force individually. So, the first one is the aerodynamic drag. Now, in this aerodynamic drag, as I told, this you can see in the picture, the vehicle is moving in a line and you see some air waves, that is, it is actually hitting or overcoming the force that is exerted by the air. So, this overcoming force which is required by the vehicle is called the aerodynamic drag, and this aerodynamic drag is generally expressed as half rho AF CD V square, where rho is the density of the air which is expressed in kg per meter cube, AF is the vehicle frontal area, that is the area of contact with the air in meter square. The next one is the V, that is velocity or vehicle speed in meters per second. The next one is the CD, which is the drag coefficient, and this aerodynamic drag rho, it is a measure of how much mass the vehicle has to push out of the way to travel through it. A is the measure of area that the vehicle is presenting to the air, and if the vehicle is put in front of the backdrop and looked it from the front, A is equivalent to the two dimensional area of the backdrop that would be blocked by the vehicle, and the bigger the area, the more air needs to be pushed out of the way to get through it, and this you can easily observe in a two-wheeler, three-wheeler and a four-wheeler. A two-wheeler has a less area of contact with the air. So, the power required or the force required to overcome that air is less. when compared to 3-wheeler. Similarly, 4-wheeler needs even more pressure or force to come across or overcome this air. And in case if you consider a bigger vehicle like a truck or a lorry, that even needs, since the area of contact is even more, the aerodynamic drag or the force that is required to overcome this air will be even higher. And CD, it is the function of the circumstances that a vehicle finds itself in, including its velocity. What we do here is, to simplify the analysis, CD generally it is given as it is treated as a constant for a given vehicle. That is, CD is fixed for some vehicles, like it may be some value for car, some value for 2-wheeler, some value for 3-wheeler and so on. We will see that when we come across the further slides. And FAD is the force that is required for the car to push the air out of the way. So, in other words, the force required to change the momentum of the air in front of the car is nothing but your aerodynamic force or the aerodynamic drag. And this pressure, this figure depicts, as you can see, when the car is moving forward, there will be the high pressure air or high pressure area will be on the front, whereas a very low pressure area will be on the back. This is because already the air has, the front part of the vehicle is hitting the air. So, when the air is getting hit, it is dispersing, and the back side of the vehicle does not have more air pressure. So, that is what is shown in this. And the aerodynamic drag, generally it is composed of 85% of the turbulent airflow around the vehicle body, 12% of the friction of air over vehicle body, and 3% of the vehicle component resistance, which is from radiators and air vents. And the typical values, as I said, the area, the coefficient of drag is fixed, and also most of the cases the area is fixed. So, it is shown here for different 2-wheeler, 3-wheeler and other types of vehicles, and these are almost maintained constant or within that range throughout our calculations. And coming to the next one, that is the rolling resistance. So, the rolling resistance, it is nothing but the force that is required to overcome the air resistance on the road surface that is caused due to the friction. And there are many things that can contribute to the rolling resistance. The primary component of it is the hysteresis, that is, as the wheel rolls along the road, the wheel is constantly being deformed, which causes loss of energy in the form of heat, and it is generally given by FRR, which is mu RR into mg, where mu RR, it is the coefficient of rolling resistance, m is the weight or mass of the vehicle in kg, and g, you know, as it is the gravity, and also mg can be thought of as the weight of the vehicle in newtons. And the harder the vehicle it is pressing down on its wheels, the more those wheels are likely to deform, resulting in greater rolling resistance. That is, when you have a vehicle moving and the more pressing is happening on the vehicle, that is, the more load is being carried out or carried on the vehicle, the deformation will be more. Deformation is nothing but how much pressure is applying on the tire onto the ground. So, this, if it is more, the value of rolling resistance will be more, which means you need a higher force than the previous one to overcome this rolling resistance. This is what you can observe when you are carrying a heavy load. The force that is required needs to be more than usual when you are having heavy loads. This is what here. And second case, it can also be sensed in the other way, like in case if the air pressure is less in our tires, the deformation will be more, which needs or which consumes more fuel to overcome that, that is, which requires more force to overcome the load resistance, rolling resistance. And in mu RR on general tires is 0.01, which means the force required to move a load on those tires is 0.01 times of the weight on that load. So, in case if you consider the load in pounds, it takes only 1 lb of force to move a load of 100 lb on wheels when with mu RR of 0.01. So, here you can see the pressure distribution in the contact area, how it is varying from normal pressure distribution to the deformation. So, when it is loading, when it is loaded, you can see that pressure deformation is more or different in when compared to the normal pressure area. This deformation, as I said, it is nothing but change of the shape of the object due to physical forces acting upon them. That is, when you have more load, the stress on the tire will be more. So, the deformation or the change in shape of the tire will be more, that is what you call it as deformation. And the torque that is required here is given by P into A, that is mg into A, because P is mg, which is the normal load acting on center of the rolling wheel in Newton, and TR is the rolling resistance in Newton meter, m is the mass of vehicle, g is the acceleration constant in meter per second square, and A is the deformation of tire in meters. And the moment the moment produced by forward shift of the resultant ground reaction force, it is called rolling resistance momentum and is generally expressed as P into mu r into cos alpha, that is mg mu r cos alpha, where alpha is called the load angle. And coming to this rolling resistance coefficient, this rolling resistance coefficient, it is a function of various factors, that is, it depends on the material of the tire that is used, the structure of the tire that is used, the temperature of the tire, and the inflation pressure on the tire, and also the thread geometry along with the road roughness and road material. Now, if you see various tire companies, they are coming up with various ads where they show different geometry, the thread geometry of each tire will be different, causing or resulting in decrease of the rolling resistance and adapting itself to the road. Similarly, it is also the rolling resistance coefficient also depends on the presence of absence of liquids on the road. So, the rolling resistance, as you said, as we were talking on, it is also depending on what kind of road it is, what is the material, like it may be a tar road, the rolling resistance coefficient will be different for tar road, will be different for concrete road, will be different when there is water on the road, when there is some other fluids on the road. So, the rolling resistance coefficient, it depends on various functions, and generally the FRR, it is composed of resistance from the tire deformation approximately 90% and approximately 4% of tire penetration and surface compression, and 6% is by the tire slippage and air circulation around the wheel. And what are the typical values of rolling resistances or rolling resistance coefficients? So, when the car is on a normal smooth tar road, the rolling coefficient is too low, that is around 0.01. When it is on the concrete road, it is 0.011. When it is on a rolled gravel road, it is 0.02 and so on. So, as you see, there are various rolling resistance coefficients that are involved for different conditions of the road, and the values in the table which are shown, they are not considering the variation of FRR with speed. So, based on the experimental results, many empirical formulas have been proposed for calculating the rolling resistance on hard surface. So, if the vehicle performance calculation, to calculate the performance of a vehicle, it is sufficient to consider the rolling resistance coefficient as a linear function of speed, and the most commonly used equation for concrete road is mu RR is equal to 0.01 into 1 plus V by 160, where V is the vehicle speed in kilometers per hour. And the next one is the hill climbing resistance. So, the hill climbing resistance, so when the vehicle is climbing the uphill, what is the resistance that is acting upon? So, in case of uphill, the hill resistance is also accounted along with aerodynamic drag and rolling resistance. So, the force required to travel up a hill is mg sin psi, where psi is the angle between the normal road and the uphill. So, where m is the mass of the vehicle in kg, g is the gravity, and psi is the vertical angle of the road relative to flat in radians. And in most cases, psi is very small and it is expressed as psi sin psi is approximately equal to psi, and hence it is also given by mg into psi. So, if the vehicle is going downhill, the psi is negative because the slope is negative, and therefore, since psi is negative, the value of hill climbing resistance force FHR will also be negative. And next is the linear acceleration. So, coming to the linear acceleration, if the vehicle is travelling at a constant velocity, there are three forces that are described to form a basic model of vehicle's behavior. Most of the time the vehicle is also accelerating. So, the linear acceleration of a vehicle along a road is given by simply m into a. When vehicle slows down, a will be negative, a is nothing but acceleration, m is the mass of vehicle. So, when it is slowing down, it is deceleration where a will gradually decrease or it will be negative, and since a is negative, the value of f L a will also be negative. The next one is the angular acceleration. So, every time the vehicle accelerates, there will be a variety of rotational parts inside the vehicle that need to spun up and requires some force. That force we call it as angular acceleration. Given that force required for angular acceleration of vehicle itself and the calculations involved are significantly more difficult, and hence Larman and Lowry in 2012 and they have proposed a equation which is using the fudge factor approximately, which is approximately 5 times of the 5% of the linear acceleration. So, f omega a or f angular velocity, it is given by 1.05 times f L a is f L a plus f omega a, that is f omega a is given approximately 5 times f L a. So, f L a plus 0.05 f L a will give you 1.05 f L a, that is 1.05 times the linear acceleration. So, if the vehicle is decelerating, the above term will be negative, and as a negative force, it is required both linear momentum of the vehicle and the angular momentum of its rotating parts. So, as discussed in the first slide, that complete or all the forces together will form the total tractive force. So, the total tractive force is given by the sum of all the forces what we have studied so far, that is the first one is the aerodynamic drag, the next one is the rolling resistance, hill climbing resistance, linear acceleration and the angular acceleration. Now, we have formula separate expressions for all these terms. So, upon expanding them, we have the total tractive force is equal to half rho a c d v square, which is the aerodynamic drag, plus mu r r into m g, which is the rolling resistance, m g sin psi, which is the hill climbing resistance, and f L a plus f omega a put together, which is 1.05 m a. So, now we substitute the assumptions and approximations. So, the value of rho by 2 is approximated to be 0.6125, the value of g is approximated to be 9.81. So, substituting these values, we have totally FTE given by 0.6125 a c d v square plus 9.81 mu r r m plus 9.81 m into psi plus 1.05 m a, and this is the force. Now, what we are actually working or what we need is the power required for moving the vehicle. So, the total power is nothing but the work done over a time, that is force times the distance, and velocity is distance over time. So, the power is equal to force times velocity. So, directly we can write P is equal to F into V. So, the total power required for rolling motion is FTE into V, where FTE is the total tractive force and V is the velocity of the vehicle. So, the total it is given by PTE, the power required is 0.6125 a c d, V square was for power, and now it is c d V square into V, which turns to be V cube, and from the remaining part I can take 9.81 as common and multiply it with V, which results in 9.81 mV into mu r r plus psi plus 0.107 a, and so this is about the total power required for rolling motion. So, whatever we have seen so far, it is what are the different types of forces that are actually required for the vehicle to move, followed by what are the different expressions that are required or that are there for evaluating the forces and what is the total force, that is the tractive force, followed by what is the power required for rolling motion. So, these all together will help us understand in the scenario which or how much the power of the motor should be, how much the power of the engine should be to make the vehicle move. And this, you know, when you consider a small electric vehicle, you can easily see the difference. For example, we have two-wheeler electric vehicle, three-wheeler and four-wheeler. Now, based on their mass, based on their area of contact with the air, based on the coefficient of drag and based on the velocity of each vehicle, the power capacity of the motor capacity of each vehicle is different. Similarly, the battery capacity of each vehicle is different, and all these calculations are made using the vehicle dynamics what we have studied. So, we will see some numericals on each of the force required for different vehicles. So, first one we will have we will try to understand or calculate some aerodynamic drag for a two-wheeler. So, first what we need to remember is in case if the speed of the vehicle is given in kilometers per hour, you should convert it into meters per second. So, if it is x kilometers per hour, it is x by 3.6 meters per second, and 1 watt is also taken or is equivalent to 1 Newton meter per second. So, for a two-wheeler with a velocity of 60 kilometers per hour, if we consider from the table CD, the coefficient of drag, it is considered to be 0.9 and the area of contact A is considered to be 0.5. So, now calculating the aerodynamic drag. So, we have the formula FAD, which is equal to rho half rho AF CD V square. Now, just substituting the values, 0.5 into the rho is generally taken to be 1.2 and 0.5 is the A, CD it is 0.9 into the value of the speed, that is 60 kilometers per hour, which we have taken, and it requires some 83.3 newtons. So, FAD is resulted in 83.3 newtons. Now, in case if we reduce the velocity, so from the formula it is very evident FAD is half rho F CD V square. So, FAD is directly proportional to V square. So, in case if we reduce the velocity by half, so whatever the calculation we have done for the first one, it is 60 kilometers per hour. Now, if we reduce the speed to 30 kilometers per hour, in that case FAD will be all the terms are constant except V. So, FAD will be 1/4 of the previous FAD. So, the velocity will be reduced by half and it is FAD will be 1/4 of the 83.3 Newton, which is around 20.83 Newton. Similarly, even if you reduce the speed of the vehicle to 10 kilometers per hour, on substituting the values you get FAD is 2.31 Newton. And now, this is the drag coefficients, we are just calculating the drag coefficients. Now, once we calculate the drag coefficients, we need to calculate the other parts. Even before that, what we try to do is, we try to evaluate the power required to overcome this drag alone. At 60 kilometers per hour, we have seen that the total force, the drag force is 83.3 Newton meter into the velocity. So, the power is force into velocity. So, into velocity will give you 60 by 3.6 into the force 83.3 for 60 kilometers per hour. So, it is somewhere around 1.38 kilowatt. So, in case if your two-wheeler is moving with 60 kilometers per hour speed, the motor capacity should be, or the power that is required to overcome the drag should be 1.38 kilowatt. Similarly, if it is moving at 30 kilometers per hour, whatever the power that is required is 20.83 into the speed, that is 30 by 3.6, which results in 173.6 watt. At 10 kilometers per hour, it is around 2.31 into 10 by 3.6, that is 6.41 watt. and if we consider e-rickshaw. So, in case of an e-rickshaw which is moving at 30 kilometers per hour, the value of CD, it is taken constant at around 0.44 and A is considered to be 1.6. Generally these e-rickshaws are limited somewhere around 20-25 kilometers per hour to 40, not more than 50 kilometers per hour. So, the coefficient of drag is given, the area is given. Now, we can calculate what will be the force that is required to overcome the drag. So, it is again rho half rho A C D V square, and substituting the values we get it to be 29.33 Newton. It is at 30 kilometers per hour, and what is the speed, what is the power required to overcome the drag? It is FAD into V, which is 391 watt. For a car, if you consider, the car will have various speeds, we take the minimal or at around 60 kilometers per hour speed, and in that scenario the FAD will be around 145.8 Newton, and the power required to overcome this drag of 145.8 Newton is 2.4 kilowatt. And if the car speed increases say to 80 kilometers per hour, in that case the FAD will be increased to 259.2 Newton, and the power will be, the power required will be 5.7 kilowatt. And remember, the 5.7 kilowatt power what we have calculated, it is not for overcoming all the forces, it is for overcoming only the force or the drag coefficient or the drag force. So, the acceleration due to drag, in order to just overcome this term, the drag or FAD, we need 5.7 kilowatt power, which is very high, and if you are going at 80 kilometers per hour speed, this is what is on overcoming the drag. So, whatever we have seen today, we have seen 1, what are the different forces acting, 2, each force and its importance along with the expressions, 3, the total power that is required, how to calculate it, and 4, a small numerical on the calculation of aerodynamic drag and the power required to overcome the aerodynamic drag in all the 3 cases, the 2-wheeler, 3-wheeler, that is e-rickshaw, and the car. So, in the next class we will see few more or some other forces and how to overcome, or what is the amount of power required to overcome that. Thank you.